Hi everyone, it's project time in the workshop again, and this time I've got something a little bit different. From time to time I do a bit of surface mount PCB assembly and repair, and I usually use my Attained rework station, my hot air rework station. You know, and that's great for a small amount of assembly, and it's okay for repair, but it's not much good when you've got an entire PCB to populate with surface mount devices. So what I really need is an SMD oven. So rather than buy one, what I thought I would do is, which quite a number of other people have done in net, is convert a toaster oven into an SMD oven. So that's what I'm going to do. Okay, here's the toaster oven I've bought off of eBay. As you can see, it's quite a small unit. It's a 9-litre oven, and I think it's about the right size that I need for SMD rework. It's actually quite deep. It's got a bulge at the back, so it can take quite long boards, I think. And of course it's got the glass door there, so we can see what we're doing. And you've got some controls on the right hand side. So what you've got in the standard oven is you've got 2 heating elements on the bottom, and you've also got another 2 heating elements on the top there. So obviously I'm going to make use of them, but what I'm actually going to do is I'm going to rip apart the existing controls. I don't need them. You've got a selector switch here for selecting which elements you want, either bottom, top or both, and you've got a timer switch, also a mechanical timer switch there. I'm actually going to do away with all that, so I'm going to rip all that out. I'm going to put my own faceplate on there with my own controls, but more about that later. So basically it's going to be Arduino controlled, which is going to control a solid state relay, which is then going to I switch the elements, the heating elements off and on. So probably within the side of the unit there, when I take the cover off, hopefully I have enough space there once I've ripped out all the existing controls and hardware. I should have enough space in there to house my power supply, my Arduino, solid state relay, etc. So that's where that's going to go. So I've been pulling together the parts have been needed. So I've got the 25 amp solid state relay, PCB, Arduino Nano, and a few other components, like push switches for the front. I'm going to have 3 of them, and I'm actually going to have an LCD. So I've actually chosen one that should fit on the front panel there. So before I start ripping the oven apart, I thought we'd go through some of the theory of exactly how I'm going to control the temperature of the oven. Okay, so what we've got here is a reflow profile for a particular paste using leaded solder. As you can see, it's a little bit complicated. It's not just a straight line graph. There's a few distinct areas that the temperature must follow over a given period of time. You can see that the actual reflow zone itself happens when the temperature is somewhere between 210 and 225 degrees C. But what we have to do is get the PCB and all the components on it and everything up to the start temperature, which is approximately 180 degrees C. You want to get everything up there pretty evenly and gradually. You don't want to burn anything or anything like that. So that's what happens in the first 180 seconds. It's called the preheating zone, the latter of which is the heat soaking zone. Once you reach 180 seconds, everything's at a nice even temperature, around about 180 degrees. You then want to enter the reflow zone, which reaches its peak nice and sharply between 210 and 225 degrees C, and then from that point onwards there's a nice sharp cool down, where roughly below 180 degrees C you're pretty safe, everything's stuck on the board. So basically I'm going to use my Arduino to follow this profile here. Okay, so as I said before, I'm going to use solid state relay to control the heaters inside the oven itself. But what I've also got is a 400 degree K-type thermocouple here. You can see it's actually got a nice threaded panel, through-hole panel mounted fitting there, so that'll be good. So basically this will interface to the Arduino, and I'll be able to monitor the temperature inside the oven at all times. And because it's 400 degrees C, it more than covers the temperature that I'm needing inside the oven for reflow, which is around about a maximum of 225 degrees. This one will cover it nicely. So what I need to do is interface the thermocouple to the Arduino. So I'm going to use an analog devices chip. It's an AD595. It's a 14-pin DIP package, and it's about as simple as you can get in terms of hookup. So as you can see here on the sample diagram, you've got the thermocouple interfacing directly onto pins 1 and 14 of the chip. You basically give the chip a 5V supply, and then on your output you basically got 10 millivolt change per degrees C. And there's a table here which shows you the thermocouple temperature and the resultant millivolt output from the AD595. And looking at the range on the table, at 20 degrees C, which is roughly ambient, I'm getting about 200 millivolts out. Then up at say 220 degrees C, I'm looking at 2.213 volts. So you're getting roughly a 2 volt change across the temperature range that I'm looking to monitor, which that 2 volt will interface nicely onto the 10-bit input on the Arduino. So how am I going to get the Arduino to follow this reflow profile? Well, what I'm going to do is I'm going to create a couple of tables in the Arduino, which I've put down basically on a spreadsheet here. You can see the time in 5-second steps against the temperature I want to follow, all the way from 0 seconds all the way up to the bottom here where it's at 240 seconds, which is the end of the profile. So you can see the temperature rising up following the profile graph, and then the reflow at this section here where you're attaining your 220 degrees maximum, and then the cool down period, the second half of the reflow, where it cools down to 180 degrees, and at that point there, after 240 seconds, I'm basically finished. So against that, I've managed to map the voltage that I should get back from the AD595 all the way down here, and I've converted that into the 10-bit number that the Arduino will see, this the code will see there. So basically I'm going to have the 3 parts to the table probably, or at least 2, the time, the temperature and the counts basically, and basically by following that in my code, against time, I'll be able to decide whether the relay should be on or off, and that way it should follow the profile. Of course, the one thing I don't know is at the moment anyway is the difference in what difference different paste will make, or even different solder will make to the profile. So it may be the case that I have to provide a way to tweak, or possibly provide a number of different profiles in the software and an ability to select them. So by using the LCD and the push buttons I'm going to put on the oven, I think I should be able to put in some code to switch between different profiles. So before I start assembling the circuit board containing the Arduino and the AD595, I thought I'd breadboard the 595, is what I've done here. And I've hooked up the thermocouple, I've sorted out the I/O on the chip itself, and I've got it running off of 5 volts. And as you can see, I'm getting about 218 millivolts output from the AD595, which on the table, let's see here, somewhere between 20 and 25 degrees C. That's somewhere between 200 and 250 millivolts there. And the actual temperature in the workshop, it's about 23 degrees. So yeah, it's somewhere in between those values there. How accurate it will be, I'm not too sure, so I may have to have some kind of fudge factor of way of tweaking so that I can, follow the profile more accurately. So if I put my finger on the thermocouple, you can see the voltage output rising pretty fast there actually. I'll release it again and it should start coming back down. The AD595, it's actually quite flexible. You can give it single or dual supply. You can turn it into a one-stop controller. It's got you can built-in set point adjustment and all that sort of thing in it. But I'm not using any of that. All I'm wanting is a straight thermocouple to voltage conversion, basically, and I'll interface that directly to the Arduino itself. You can put a bit of averaging and that sort of thing on the 595 itself. However, I think I'm going to do that in the software. I've got some quite good routines that I've used before for averaging and to smooth out any bumps along the way in terms of the signal coming into the Arduino. So we'll see how we get on with that. So before I get stuck into the assembly of the board I'm going to put inside the toaster oven, I really need to open up the oven and see if I've got enough space for this size of board, see if I can actually rip apart the front, that I can mount my LCD, all that good stuff there. So before I do anything here, I think we'll open up the oven. Right, that's the cover of the oven now, and I've exposed the right hand side here. We can see the wiring. First thing I notice is I've got quite a bit of room in there, so I think we're looking good in terms of having an area big enough to house my transformer, my circuit board, my solid state relay, etc. So it's pretty simple design. You've got the 4 heating elements there. They're just seriesed up at the back end there. So the top 2 are in series and the bottom 2 are in series there. Basically you've got the selector switch there for selecting which heaters you want to have on. You've got the timer, the mechanical timer relay there, and temperature switch there, and that's about it basically. So obviously I'm gonna rip all this out. I'll retain some of the wiring because this is nice heat resistant wiring there, so I'll retain some of that. I'm also going to retain the temperature switch. I don't know what temperature rating it is. I'll have to get it off to have a wee look at the numbers on it, but I'll probably retain that because I think it'd be a good idea from a safety perspective in case there's any kind of over temperature on the oven itself. So I think the first thing I'll do is I'm going to rip out the front panel here and fabricate my new one. Mount the LCD and my push switches, etc. And it looks fairly easy. There's 6 screws which appear to hold on this front section here. So once I get that off, I should then be able to disassemble this, or if worst case, cut this section out here, and I'm going to put my own aluminium plate in there in order to mount my LCD. So that's the control panel removed from the oven. You can see the timer switch there and a little bell on the back, and the selector switch there for the elements, and the lamp in the front. So I think the first thing I'll do is remove these selector switches and see how I can go about either routing out the holes for the LCD and my switches, or I don't think I'll be able to cut this out. I think it'd probably be easier if I just cut the holes that are required for the LCD to fit through, and possibly put another little aluminium panel. There's actually a recess in here, so I think my own aluminium panel will sit in there pretty nicely without actually having to remove the whole area. But I'll see how I get on. I might just do that because there is actually screws in the back here which hold it in place. So I'd have to cut around them as well. So we'll see how we get on with that once I remove the switches. I've managed to remove the bits and pieces from the back of the control panel, and this is what it looks like now. I've fitted the LCD and fitted the 3 push buttons that I need, and then also in order to fill a hole vacated by the neon, I've fitted my own LED, and there's it from behind with the LCD in place. I'll probably put a little ribbon cable from here off to the Arduino, and of course the same with the switches interface. So that's a bit Heath Robinson, but I think it'll do the trick nicely. Okay, a bit more progress now. I've fitted the panel back on, complete with the LCD, push buttons and the LED. I think it looks not too bad. Going around the back, as you can see, I've run a ribbon cable up to the header on the back of the LCD. I've not been able to fit the connector on the header. It's too close to this panel here. But I've managed to solder it on okay, it's fine, and I'll put a connector on this end once I get one. And as you can see, there's the back of the switches and the LED, so that's perfect there. One thing I've started to think about is the heat that's generated from the oven, how much of it's transmitted through into this chamber here. What I've decided to do is I'm going to make another aluminium panel here as close to the outside edge of the panel, and mount the Arduino etc. on this side, so the aluminium plate will act as a heat shield, so that I've got the the low voltage stuff on this side. The solid state relay, probably mount it on the other side and keep all the high voltage stuff that side. So another thing I'm going to do is probably get some more of this high temperature wiring and the connectors and use them on the solid state relay as well. Okay, we're a little bit further on now. What I've gone ahead and done is, I didn't like the mechanism whereby when you opened the door it pulled the tray out here, or a certain distance anyway. I didn't like that idea, because what it meant was on the side there's these slots here, and they're actually clean through, so any heat inside the oven just is going to come right out the side here into the side here, and that's not so bad at this side. But on the other side where I've got the electronics, I didn't really want any heat escaping into that area here. So what I've gone ahead and done is I've just modified it and put some simple L brackets on there, and they cover the slots up, so therefore you can't see, there's no chance for hot gases or hot air to come through there. And at this end I've done some work as well. The main thing you'll see here is I've put some fireproof matting on the side here, just basically to try and insulate the heat from coming through to the electronics. What the matting was, it's one of those mats that you can buy that plumbers use on their gas torch when they put it behind pipe work when they're soldering up plumbing fittings. So basically I cut that to suit, and I've fitted that there. I've also fitted the pillars here for mounting my base plate onto, which will hold the transformer, etc. It'll stand off about 10mm from the side of the oven, so there'll be an air gap down behind as well, so that's that's good for the insulation. So the actual here's the actual plate itself, so I'll just put that in a position just to show you. So here's the base plate in place, so as you can see, and I've got a gap down here, an air gap down there in front of the matting, so I think I'm doing basically all I can do to stop any heat being transmitted through onto the actual electronics itself. You can see the cutouts around the elements there, and also the temperature switch at the side there. Transformer is a perfect size. It's it's perfect, and there's another 8mm or something like that between the top of the transformer and the side of the casing, so that's fine. The Arduino will be fitted on here on this bit of Vero board here. I've mounted that actually on purpose towards the rear of the oven, as close as it can be to this vent. I'm thinking that's going to be the coolest area and the best chance possible to keep any temperatures down on the actual Arduino itself. That's probably going to be the most sensitive of the electronics. Certainly the transformer and the relay shouldn't be too bad, but the Arduino and the 5V regulator I want to keep as cool as possible. So the ribbon cable here from the LCD, I'll route that down and around and then onto the bit of Vero board there. I'm just waiting on a connector come in there, and then I can it'll be simple, just onto the PCB there. That's the thermocouple now fitted to the inside of the oven, about mid-height up the side. I think it's probably the best place for it, round about level with the PCB, near enough. I'll zoom out, and that's it coming through the side there, and then I've run the cable along the top, and that's it, just dangling here, ready to be fitted. I've also started work on assembling the Arduino board there. That's the components all laid out on it. Just got to wire up the back of it there. There's 3 connectors on the board. The one at this side here, the two-way one, that's the 9V AC secondary from a transformer. Just a nice little short run there up into there. The 2 at the bottom, that's for the thermocouple, which will route round and into the connector there. This one here, this 8-way, that's going to interface with the front panel switches and the LED that are out of sight there. Okay, the next stage is to start doing some testing on the Arduino board here. I've done all the wiring on the back of the board. I've got all the components fitted. I've just received the IDC cable for the ribbon cable, so it's hooked up now, and I just thought I'd offer some sort of hints and tips and sort of procedures you would go through when powering up any new board, really. The last thing you'll be doing is populating all the components on, building it into your unit, and then switching on the power. You never really know where you're going to have problems, especially with homemade boards like this. A simple mistake in the back of the board, swapping over a supply, a chip or something like that, and you're just going to see smoke. So just to let you know, what I've done here is basically I've beeped out the supply from the Arduino 5V supply around the board and up to the LCD as well. You can't see that in the back there, but I've beeped that out with the meter and the 0V connections as well. Made sure all my capacitors, etc., decoupling capacitors are the right way around. And then, rather than hook up the secondary AC from a transformer direct into the board, I'd rather supply it with an independent power source, a controlled power source first, just to make sure that the Arduino powers up okay and the LCD powers up okay. So in this case, because the LCD's low power, and basically the only other 5V component on the board is the AD595 itself, which I haven't plugged in at the moment, then I've decided just to hook up the USB cable to my laptop here, and it will generate the 5V for the Arduino around about it. It's usually just a bit less than 5V actually, given the cable length, etc., from a USB cable. But basically I'm looking at 4.8V at the Arduino itself. That will then allow the LCD to power up, and also the AD595 once I plug it into the board. But for the moment, all I've got is the LCD and the Arduino. The test cables that you're seeing here are basically just hooking up my meter, and I've got a voltage source from a homemade voltage source here, simulating the output from the AD595. So let's power it up. Okay, I've already had it powered up previously, but basically there's the LCD working there, and it's following the power up sequence that I'd written into the code. One other thing to remember is with these LCDs, there's usually a contrast pot that you have to wire up yourself, so there is actually a pot on the board, and I've already set it up so that I'm getting a display. Quite a common problem for beginners is they'll hook up the LCD, they'll get their code written, and they'll end up troubleshooting the code over and over and over, trying to see why their LCD is not doing anything, and it's usually because the contrast is right down and you end up with a blank display. So anyway, there we go. I've got the LCD running. It defaults to oven off mode. I haven't hooked up the switches yet, so what I'm going to do now is I'm going to pull the pin on the Arduino that'll simulate the pressing of the mode push button, which is not going to start the oven at all. What it's going to do is display the current temperature from the temperature probe. I've got the temperature probe hooked in, the K-type's coming into the board here, so it should be, it would be working once I put the chip in. But like I said, I haven't plugged in the AD595, and I'm using a voltage simulator to simulate the AD595 and the thermocouple. So let me just ground T12, that's that there, and you can see on the display I've now got temp 0, so that's temperature in degrees C. It's pre-calibrated. I've set it up already in the software, so basically all I need to do now is simulate the table here. For instance, 200 millivolts will give me 20 degrees C, and then all the way up to basically 4.057 volts is going to give me sort of 400 degrees or thereabouts. So let's wind the voltage source up. I'm doing that off camera, and I'll put it up to about 200 millivolts. So there we go. It's just under, so it's 190 odd millivolts, and that's giving me, oh, oops, cable's jumped out. Put it back in again. There, so we're reading just about 20 degrees there. I've got, like I said earlier in the video, I'm not doing any filtering on the millivolt signal from the AD595. What I'm actually doing is I'm doing that in software. I've got a nice little averaging routine, a rolling averaging routine, which I've used in a number of other jobs, and it's really good. What it basically does is, if, for instance, the voltage output of the AD595 or the source suddenly jumped from maybe like 1 volt directly to 2 volts, it doesn't mean that you'll get a jump on the display. For instance, if it was wanting to go from 20 degrees directly to 100 degrees, it would go 21, 22, 23, 24 pretty fast, but it would ramp up to that. It's almost like an integrator routine in the software, but basically what that'll do, and what that's given me, it's more than just averaging. You're losing any spikes. You're completely getting rid of any spikes because they are mapped out because of the integrator. So there we go. I've got the voltage source there at 200 millivolts, and it's reading 20 degrees C on the display. So I'll just wind it up, and it's reacting quite nice. Basically, the mode push button, I've got it configured. All it does is basically put the system into read mode, basically just to read the temperature on the display. It's not doing any control over the heaters or anything like that. So I just thought it was something extra to add in. Okay, with that done, I think the next step is to actually plug in the AD595. I've already tested the socket on the PCB that the correct supply is going to the correct pins, so it's just a case of disconnecting the voltage source and plugging in the AD595. So let's do that now. Okay, that's AD595 plugged in. We're ready for a power up. I've got my multimeter set here so I can probe the output from the 595. So let me plug in the USB cable to Arduino and see what happens. Okay, so oven's off, so let me just simulate the mode switch. And the temperature is 0 and it's jumping about a little bit there. Looks like a little bit of noise or something. So first thing I'm going to do is get the supply of the AD595. 4.77 volts. I haven't checked the spec of the chip itself, but you know that is a little bit low, but if it's just typical of any other IC, then I would have thought it would have been okay at that, but I'll double check the datasheet. And then the output from the AD595, you're looking at, you can see it jumping around there, so anywhere between 80 millivolts and down to 40 odd millivolts. And according to the datasheet, that's going to give me anything from the, looking at the datasheet now, 0 up to 10 degrees C, something like that. And it is jumping around, just jumping about. Okay, that's the 595 hooked in again there. I was getting nothing out, I was just checking off camera there, I was getting nothing output from the 595, and I did a little troubleshooting, and there goes a little schoolboy error. I had marked on the terminals here, on the, I don't know if you can see that, on the back end of the terminals here, a plus and minus to signify the polarity of the K-type thermocouple, and I'd actually written it on back to front. What you've got here is pin 1 is the positive output, positive input, sorry, to the IC, and then pin 14 is your negative input. I think it does say a little bit more detail on this page here. Basically, there you go. Pin 1 is your positive, and pin 14 is your negative. However, if you look a little closer, you can see that the one side of the K-type is to be grounded, and that's actually the positive side of the K-type. So I just automatically thought it'd be the negative side of the K-type that'd be grounded. So therefore, all that just got me to wire up back to front on the terminals there. So I've corrected that, and I've just powered up. And if you look on the meter here, I'm getting about 266 millivolts output, and that's just over 25 degrees C according to the chart. So and I've got the Arduino's running, oven's off at the moment, so let me just simulate the mode switch, and just get a cable here, simulate the mode switch, and let's have a look at the readout. There we go. And that's 26 degrees, 25, 26 degrees there, which is about right in the workshop. So it's maybe slightly high. I'm about 23, 24, so it's maybe reading slightly high. If I want it to be, you know, totally accurate, I might need to fudge the figures a wee bit in the code, just to correct for that. However, I don't really know what sort of temperature I'm getting inside the oven. It could be a little bit more. So let me just get. I do have a digital thermometer here. Let's see if I can get it running. I'll leave it a minute to settle down. According to this, it is about 22 degrees. I'm just probing right next to the, what's it going up now? I'm touching the thermocouple here. So that's about 23 degrees inside there, without leaving it much room to settle. And I'm almost exactly 250 millivolts there. and that's 25 degrees according to the table, so I am slightly out. I don't think that's too bad considering it was a bit of guesswork on the software to create the table. But the inaccuracies of the Arduino probably a little wee bit there. Could be something to do with the fact I'm running the Arduino off just less than 5 volts. But once I get it powered up off the proper power supply, and I'm generating a good stable 5 volts from the onboard regulator on the Arduino, hopefully I can, if need be, trim that in the software. So I think the next thing to do anyway is I'll get the heat gun and I'll heat up the thermocouple and see if we can get that temperature to rise. So I'm just going inside the oven here with a heat gun. I went up to about 48 degrees there, 475 millivolts. So back to the board again. So I think I'm quite happy that it's wired up okay. I think the next step to do is I'll disconnect all my test wires here, and I'll start work. Just come around here and have a look. I think I'll start work on the power supply and get it all wired up. I've received some high temperature sleeving here, so that's going to go over all my wires that I'll use to hook up the primary and secondary on the transformer, and also all the connections to the board here. All the connections to the I/O terminals here will all be covered in that high temperature sleeving, and of course up to the heater terminals as well. So I think I'm ready to start working that now. Okay, I thought I'd just show you the PCB here. Arduino Nano, I've used them in quite a lot of projects in the past already. I quite like them because they're small, they've got the full complement of I/O, you know, compared to the Arduino Uno, but you've still got the a real USB connector here rather than perhaps a single inline header that you've got to go and solder up onto. So I quite like the Nano. You've got AD595 there. You've got a small little PCB buzzer there. It's driven by a small FET. I think we're up at 30-40 milliamps for driving the buzzer. So whilst a digital output in Arduino is capable of that, I thought there's no harm in just putting a FET in there just to drive it. You've got the bridge rectifier here, a nice little slimline one there. I think it's rated at a couple of amps. You've got decoupling capacitor on the output of the bridge rectifier. You've got a cap here across the 5 volt supply of the AD595, and then hidden under there you can see another cap. That's again on the 5 volt supply across Arduino. So you've got the thermocouple input here. I've already reversed the plus and minus per the error that I'd made earlier on. We've got a pot here for the contrast adjust on the LCD. And of course you've got the header there for the LCD, the dual inline header, which the ribbon cable just plugs straight onto. And you've also got the I/O along the top here for the push switches, etc. And you've got the input here, which is a secondary output of the transformer. So you've got basically a 9 volt supply coming in here, AC. So on the back of the board, just wire wrapped as per what I usually do. The heavier wire here is on the basically the supply coming in on the bridge rectifier and the cap, and I've beefed up the tracks there with a layer of solder there just to increase the current handling and keep the resistance as low as possible. All the other, the red colour there is basically all just the I/O to the Arduino. There is another colour there, just the yellow there. I just used that that's the thermocouple input. I just used that to better distinguish that when I'm troubleshooting the back of the board. So it's basically just a, you know, a bog standard sort of like wire wrap prototype board. Right, we're at the testing phase now. I've more or less completed all the wiring and the assembly of the oven. So I'll just take you around what I've done. I've made some modifications. What I've actually done is I've changed out the existing heating elements that came with this particular oven, because I'm finding that they were just too slow. They just weren't powerful enough. They were just a bit too slow. So I happened to have another oven lying about, one that got damaged. But the heating elements were in pretty good nick, and they're a completely different type. So I've retrofitted them to this unit here. They fitted not too bad, including the insulating elements, insulating bushes at the end there. They sort of fitted pretty well. Did have to open up the holes a bit, but they do seem to fit quite well. There's just two of them. In the original oven it was one at the bottom and one at the top, and I just kind of thought, well, I'll just fit them both at the top and not have anything at the bottom of the oven, because, you know, I'm not toasting bagels, you know, I'm heating up a PCB, so, you know, primarily it's going to be the top side that's wanting you know, most of the heat. So I figured that's what I'd do here. And as you can see there, I've got my thermocouples fitted as well. I've fitted some stiff wire along its length, and it actually gives me some flexibility to move it around, and I can bend it to the position that I'm wanting to you know, to target. As you can see, the end's got a little bit brown there, but that's just during my first tests. The oven was just a tad too hot, but more of that later. So basically, yes, that's the inside of the oven. You can see that there's some capped on tape in and around covering some of the holes there. I'm quite surprised with the capped on tape. You know, it's resistant to heat, but I didn't think it was as good as what it was. It doesn't even fold or melt or curl in any way, shape or form, so it's really good stuff, the capped on tape. So that's that fitted there. So coming around the side here, you can see this is the two heating elements in series here, so some nice heat resistant wire there. That's that end there. Around to the business end, and of course I just had to rewire it as necessary for the two elements at the top here. Makes it a little bit simpler there. One other thing I have fitted as well, well, a couple of things I've fitted. I've fitted an AC socket complete with built-in fuse and switch on the back of the unit there, which went in rather nicely. And I've actually also fitted a fan, a 12 volt DC fan at the bottom here, which is pulling air from the outside up through the vent holes at the bottom of the oven there, and it's basically just to try and cool the electronics. You know, it runs warm at this end, but it's not hot. But I really don't know what it's going to be like with the actual metal cover fitted on the unit. If I was going to do it again, I'd probably actually put a thermocouple or something at this side and use another analog input on the Arduino, but no, it's too much trouble there. So, but yes, I still have the thermal switch as was fitted to the original oven, and that's still fitted on the side there. That actually tripped the other day when I was doing some testing. I had it running far too hot because the profile wasn't, you know, too right in the software. So I've run it. I've given it one full run with a test PCB inside the oven, and this was the result. And I think you can see it was rather toasted. So I think the profile was a bit too high. What I'm finding is that the position of the thermocouple does make quite a lot of difference. And originally, during this test with this PCB, I actually had it. I didn't want it to be in free air. You can get a lot of difference between a thermocouple recording temperature in free air as opposed to against a piece of metal. So actually, tried all sorts. I've been having it through a metal plate inside the oven with a tiny wee hole in it, and putting the end of the thermocouple touching the insides of the hole, so I'm actually measuring the temperature of the metal. but I wasn't too happy with that. I'm just trying to, you know, fiddle around here and see which the best result is. So at the moment I'm testing it with the stiff wire through the thermocouple here, so that I can move and bend it around, and I can position the you know, the thermocouple where I want it to be. Going back to the PCB, you can notice that there's a, you know, there's some dark areas and some light areas. The dark areas, I had it sitting on top of this U channel mounted the other way, and the light areas is where the metal was sitting against the PCB. So all I can presume there is that the alloy that was sitting against the light areas was soaking heat out of the PCB, and the areas that were dark were overlapping into free air, and basically it was just the board was heating up. So it's something to think about. So what I've done here is I've put the metal on its end, on its side here, with a nice flat side at the top, and the idea is that the PCB will sit on the top there, and you know, the alloy can maybe soak the heat out of the PCB. Of course, I don't want it to soak too much heat, or I'll not get the SMD reflow effect. But it's something I can play about. With. And then the idea is that I can lay the PCB just directly under the thermocouple there, or move the thermocouple around. But whether that's the right thing to do or not, I guess it's just a case of, well, we'll suck it and see. Okay, we're back at 29 degrees again here. I think it's low enough to retest, so let's try again. I've adjusted the profile, I've extended it by 40 seconds, the soak period basically, which will extend the reflow period out. So instead of being 180 seconds, it's 220, and it obviously has a knock-on effect, so now we'll have 250 and 280 for the full reflow zone. So let's try that. PCB in. I've also, just as a little test here, this is actually an existing board. It's already been reflowed, so I don't know what will happen here, but there was an actual unpopulated IC on this board, so I've actually found an old SMD op-amp which almost fits the same package as the layout of the board. At least 4 of the pins do, so I've put that on with a bit of paste there, and we'll just see what happens with that. Okay, and ready for the test. So again, I'm monitoring the temperatures here as it goes up. I was quite happy with the preheat zone that's prior to the soaking zone. And I think it probably started to be a bit under temperature at around about the 120 seconds into the soaking zone. So hopefully by extending it, it'll allow the temperature to creep up as it should do. The only thing, it'll be a little bit worry if I'm extending everything by too much. I'm subjecting the paste to too much heat and possible chance of evaporation, that sort of thing. So we'll have to watch out for that. So here we are at 100 degrees, and it's around about 80 seconds. To the soak zone at the 90 seconds bang on. One thing I'm keeping my eye out for is any signs of any kind of smoke or anything like that coming from the oven, and there doesn't appear to be anything. I'm using high temperature sealant in and around various holes that I've plugged in the oven, and also of course the Kapton tape, but everything, all that seems to be okay. So it seems to be bang on temperature at the moment because the LED is going off and on as it turns the heaters off and on, so it must be following the profile reasonably well. And it's due to go into the reflow at 220 seconds, which should be 180 degrees, so we might be slightly under that still. There we are, 166 degrees, so a little bit under, but we'll leave it run and see what happens. That's into cooling now. The Vero board I can see inside's not moved, it's still dry, but looking at the op-amp on my circuit board that I'd actually put the IC on, it looks to be, it looks like it's reflowed. So maybe I'm missing something when I'm doing my little test with the paste on the Vero board with a little bit of solder. Then we'll let it finish the cycle, another couple of seconds. And that's us finished there, so I'll open it up. Carefully remove the board. So as you can see, I've reflowed this side of the 8-pin op-amp there on 4 pads that were on the actual PCB. As you can see, the op-amp wasn't actually long enough to reach the other side, but this 4 pads here, I just dabbed a little bit of paste on each pad, laid the IC onto it, and it's reflowed perfectly. Okay, having just completed that reflow test, I've disconnected the power, so we're dead at the moment. I just thought I'd feel in and around the components and transformer, relay, etc. inside the end here to see what my temperatures are. I would say the relay is warm. It's not hot. It's just warm. The transformer, I would say the metal casing's warm to touch as well. The Arduino and the IC, it's cold. It's not really heated up at all. In fact, the IC feels cold to my touch, having just put my fingers on the transformer and that. So everything seems okay. Of course, the top here, the oven, actually it's roasting hot. It's absolutely roasting hot there, which that's to be expected. So I think the next step is what I'll do is I'll put the cover on, I'll run another test, a full reflow test, and then take the cover off and see what sort of temperature I've got inside this area here. Because what I think might happen is, due to the heat build up in the top here, it's going to flow to some extent round the corner into where all the electronics is. Like I said, it's not going to cause too much of a problem. I am using, well, on the AC side anyway, the high temperature wiring. It was from the original oven. I managed to rescue that, and I still have the thermal switch there, which I'll cut out, if things get too hot in the oven. But obviously the ribbon cable and all the DC cabling, I have to make sure that that's safe, and it appears to be at the moment anyway. Okay, I thought I'd show you the Arduino software that I've written for the Reflow Oven. Basically, this is it here. I'm using two libraries, obviously one for the LCD, and I'm also using Timed Action. Timed Action is a really good library. I've used it quite a lot, and what that enables me to do is very easily, for instance, run subroutines at specific timed intervals. And from that you can do a whole host of things. So I'm actually using that for refreshing the LCD and that sort of thing. It makes it very easy. You can concentrate on the rest of your code and not have to worry about that. So that's what that's for. Obviously to set up the LCD here, and this two lines here, the two arrays that I've set up here, I did originally have the code set up so that in order to follow the profile for the paste and solder, I actually had a whole load, maybe about 100 numbers in the array for it to follow, and it got a bit laborious when I wanted to adjust the temperatures, and shift them all in one direction or the other direction, so it became a bit laborious. So I actually changed it to what you see here. There's basically just 5 numbers in each of the arrays there, and basically it'll do y equals mx plus c between each pair of numbers. So therefore you get a straight line graph from on the temperature one here. It's 20 degrees up to 150, so you'll get a straight line graph between 20 and 150 degrees over the period of 0 to 90 seconds, and then obviously from 150 to 180 it does the same, and that's between 90 and 220, and that's all the way and so on up to the end point, which is at 280 seconds. We should have cooled down at the end of the reflow period to 180 degrees. So it enables me very easily to adjust the temperatures. You saw in the tests I did there, I had to increase the soak zone, which is between 150 and 180 effectively. So I actually adjusted the figures there so that it extended a little bit further, so it was very easy to do. So just got some variables that we're declaring there. I'm also using an averaging formula, but we'll come on to that in a little minute. Here's the actual timed action, setting up the variables for that. So the 40 here means run at a timed action at 40-second intervals. So there's a subroutine further down called timed action, and it's basically called automatically every 40 milliseconds. So let's go further down there. It's just a setup of all the I/O, the setup of the LCD, some other variables there, and then we've got the main loop. The main loop's actually very small. We're doing the timed action check. That's just setting up and running continuously the timer, the timed action. And here's the actual timer service itself. So this is the one here that's basically running at 40 millisecond intervals. So I'm actually incrementing a variable here called tick fast, and that's used later on to generate, for instance, a 2000 millisecond subroutine based on the timing from this original source one. So that's what we've got here, and then here we've got the averaging formula. What I'm actually doing is reading the analog input directly from the temperature input, and basically applying this averaging formula. It's basically a rolling averaging formula, and basically what it does is, if the temperature wants to go from 50 to 60 degrees, and let's just say there's a spike on the analog input, it'll basically help disregard that spike, because this averaging formula won't allow the variable to jump directly from 50 to 60. It'll only allow it to go 50, 51, 52, 53. Of course that'll happen pretty quickly, but you can adjust the damping effect it has with this variable here, Keyonna. So I've got it set up so it's still pretty fast, but it does manage to eradicate any spikes, that sort of thing. So I've used this formula before and it's actually quite good. We highly recommend it. And here's the one of the this is basically one of the timed subroutines, which is basically just controlling what's has been written to the LCD at certain periods of time in the software, to do the reflow, the cooling, that sort of thing. But we'll skip past that and down onto the main part here. So this subroutine here is basically, it comes from that tick slow variable, which is generated from the 40 millisecond interrupt. So as basically using that to generate a 2000 millisecond subroutine here. So this is where I'm basically looking at the two arrays and running through the profile from start to finish. And you can see basically if the degrees C is less than the step temperature in the array, it will turn on the relays and the LED, and then obviously vice versa. If it's too hot, the degrees C is higher than the step, then it will turn off the relays. So I've got no need for any kind of PID routine or anything like that. There's not going to be any chatter whereby the relay is going off and on very quickly. That's not going to happen, because basically this whole routine's running at a 2000 millisecond interrupt. So everything happens in 2 second steps basically. And the bottom part here is just controlling which parameters in the array are being used, in the two arrays that are being used, so that they're fed back into this routine here, so that it can follow the entire array temperature and timing from start to finish. And down here there's some extra routines that are relative for activating the buzzer. The quick and dirty way of activating buzzers is to just turn on a digital output which is connected to the buzzer, delay by a certain period of time, and then turn off the buzzer again. And I hate doing that, because basically when you use the delay command in the C++, you're basically stopping the program in its steps, and I just don't want that to happen. I don't think you should be doing that with any piece of software. So I've basically using the millis counter inside the Arduino to basically look after the activation of the buzzer for me. I just tell the buzzer to activate, and the software will carry on, and after a certain period of time which I've specified, then it'll turn the buzzer off automatically. So I've got one or two different setups here for depending on how long I want the buzzer to activate. So therefore, if I call buzzer activate 1, then the buzzer interval will be 50 millisecond. If I call buzzer activate 2, then it'll be 1000 milliseconds. So all I'm doing is activating setting this variable here, and that activates the buzzer automatically. So let's see if I can find one further up here. So here's one here in the middle of this subroutine here. It's buzzer activate 4. That's all I have to do to activate the buzzer, and it'll immediately carry on. It's not going to stop at any point in time. It's going to, as soon as I set that variable to anything other than 0, then it'll automatically know to go and run the buzzer routine. So that's what that's for, and that's basically the entire program. So it's not complex in any way, shape or form, but it just does the business. It seems to work okay. Okay, that's the SMD oven finished. The final testing was fine, everything's great. So I'll put the cover back on, and as you can see, it's all nice and clean. Everything's safe and working okay. I've also made sure that I've put the feet back on the bottom there, because I'm sucking air up through the bottom vent there. Obviously want to make sure that's not sitting on the ground on the deck there, so the original feet back on to give it some breathing space underneath. So that's it all working there now. And what I've done is I've got a collection of a couple of pieces of alloy here that I'll just leave inside the oven, and I can use them, I can maneuver them around when I'm wanting to sit PCBs. You get different sizes of boards, so they'll just sit inside and they'll just be the tools that I'll use with the oven. Job done.